Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones. Hi, this time around we're going to talk about solid-state LED lighting. Why? Well, I just built myself a new outdoor deck and I put a new roof over it and everything, and it's really quite cool. It's an outdoor room, and to finish it off we need to install some lights to to light the place up. And well, our old one had these old style spotlighty, these are compact fluoro G10, what do they call them? Yeah, GU10 bulbs and things like that. And we're going to use these again, but I thought, hey, why not give LED lighting a go? So I decided to give these Cree solid state LED lights a go. You've seen them, these little Cree ones. Now I decided to get basically pretty much the best ones on the market. It's the Cree X-Lamp XPG, and the datasheet claims some really amazing things for them. Things like 132 lumens per watt. It's incredible. I mean, one of these compact fluoro, this is a standard compact fluoro, and this one is 57 lumens per watt, right? Less than half. And this one here, one of these circular ones, this is 70 lumens per watt. Whereas these little tiny, itty-bitty Cree XPG LEDs are up to 132 lumens per watt. Unbelievable. And if you use these circular fluoros, these T5 circulars, they're better than these compact fluoros in efficiency, but they're still not as good as these little LEDs. Is it bullshit, or do they really work? So I thought I'd get some and try it out. So the first thing I did was take a look at the data sheet. 132 lumens per watt. That's its maximum sort of efficiency if you drive them at 1 amp. But I was only going to drive them at 700 milliamps just to be on the safe side, and also because that's a typical value you can get out of these constant current controllers that are powered from the mains. So I thought I'd drive them at 700 milliamps, and I did some rough calcs based on the old roof we had out there and the old lighting system, and it looks like that maybe a dozen or 16 of these LEDs might actually do the job. It might be good enough. So I borrowed some old Cree LEDs, these star versions, from a friend, and they're not the XPG ones, which are the latest super efficient series ones, but I got some of them as a trial. I put a couple of them on a alloy strip, an aluminium strip, or aluminum. Sorry for you US people, you don't know what aluminium is, because you've got to heat sink these things because they get quite hot. So I didn't do any thermal calculations or anything like that because those sort of things are traditionally very tricky, and well, I knew this would be plenty. It's a 25 millimeter wide aluminium strip. I was going to have them 1.5 meters long, and I was going to mount 8 of these LEDs per strip, and it's a 3 millimeter thick strip, so plenty of heat sinking, I thought. And so I wired them up, and here's some photos. And it turned out that with 16 of these Cree XPG LEDs running at 700 milliamps each, gave more than adequate light, and here it is. As you can see, it's hard to get a photo of it, but I'll take some video after this, and I'll hopefully show you it on live video to see what it's like. But it worked really well, and well, that's the end. Normally that'd be the end of the story, and I wouldn't do a blog on it because it's not very interesting. Okay, solid state lighting works, they're great, but hey, what makes it more interesting? Well, I decided to do some measurements. Now I'm here to tell you that thermal heatsink design is really tricky business. There's so many variables involved in it that it's really hard to do it accurately for all but very simple calculations. Now you would think this one would be very simple to calculate it. You've got a strip of aluminium, and you've got some LEDs mounted on there. You know the dimensions and the thickness and everything like that, and it should be pretty easy to calculate. But it's not. Trying to calculate something like this, it's not impossible, but it's very, very difficult. And I tried to do some basic calculations of this. I found some graphs which I thought were, you know, a pretty good source of data for a 3mm aluminium plate. And for roughly the surface area which I had here, which was 1.5 meters by 25 millimeters wide, I got you know, an answer of like 3 degrees C per watt, and that sounded quite large to me. And based on the amount of power I was putting into these 8 Cree LEDs on here, it wasn't getting anywhere near hot like you would actually predict from those graphs. So something was up. So I decided to take some measurements and get some data, because I love data and I love plotting stuff because it's great fun. So what I did is I attached some thermochron eye buttons. I've mentioned these in a very old blog, little temperature loggers. I attached them to the aluminium strip at various locations along, and here's a photo of the actual installation of them. And as you can see, and I used one as for ambient temperature as well, just hanging down there, and I attached them to the strip, and this is what I got. Okay, I got this data out. I did it the other night, and basically what it is temperature in degrees C versus time, and this goes from about 6 p.m. up to about 8:30 or something like that, so just over a couple of hours. Now I'll put up a more detailed image of this later, but as you can see, the ambient started out at around about 37-38 degrees. Now yeah, it was hot in Sydney just the other night. It was really hot, and then it started to, well, it cooled down a bit, and then it started to drop fairly drastically. It dropped down to like 32 pretty quickly, and as you can see, this is where I took them from inside, and the other 3 are the temperature sensors. So as you can see, these were inside, and I took them out and they stabilized, and this is where I switched on the light, and you can see it ramp up and it hits a pretty stable equilibrium here, as you'd expect. And so, you know, this didn't look too remarkable until I plotted the difference between each one of these 3 temperature sensors and the ambient. And this is what I got. Once again, I'll show a higher resolution version, and this shows the difference. So 0 degrees up to about 13 degrees was the maximum difference. And as you can see, it ramped up fairly quickly, and then it sort of stabilized a bit here, but then it ramped up a bit further, and then it did some jigging about here, and then there's a real sudden drop just about here. It's very remarkable and very sharp. Why? And why did it do that? It should basically reach a thermal equilibrium and then stay flat, but it didn't. And it took a couple of seconds thought, and then I realized, a storm came through. And it's not because the temperature was dropping, it's because the wind picked up, and the wind was causing a cooling effect on the heatsink. It was drastically increasing the efficiency of the heatsink because of the wind blowing across it, and that's why you get these sudden falls, and then, you know, these peaks and jaggies. If you're in a perfect, pristine environment, you would have, or a very controlled condition in a lab, you would have got basically a flat line, but we didn't. So I thought that was rather interesting. So I decided to do some calculations and see what I could come up with. Now, I modeled the system something like this. The TJ is the junction temperature actually in the LED itself, okay? And that's an unknown. I just wanted to know that out of curiosity. Now, PT is the total power that that LED is wasting or putting into the heatsink. Now we'll talk about that in a minute, because that's a rather curious one. Now the data sheet, if you read it, it says that the thermal resistance of the LED to its solder junction is 6 degrees C per watt. And also it comes on the LED comes on a little base. Now, I didn't use one of these star ones. I used one of these little 10mm round ones, and here's a photo of it, and they're really quite cool. And I couldn't get any data on what that actual thermal resistance of that is. But, you know, it's going to be fairly low. So it's an aluminium base, so I don't really know that. So I sort of took that out of the calculations. And then there's the thermal adhesive. I actually used a what's called an Arctic, well, it's a brand name, Arctic Silver thermal adhesive. Now, it's not a thermal paste. It's not like a heatsink compound. It's actually an epoxy, a permanent epoxy adhesive that's thermally conductive, and it's really cool stuff. Highly recommend you use it. And if you look at the data sheet for that, its thermal resistance is incredibly small. It's like 0.05 or something less than that degrees C per watt for, you know, an X micron layer film, and I don't know how thick my film is or whatever, but, you know, it's very, very low. So you can, like, take that out of the equation. And then there's the thermal resistance of the heatsink. Now, as I said, I looked at some graphs and things. I found some graphs and stuff for a 3mm plate of aluminium, and it seemed quite high at like 3 degrees C per watt or something like that. And I thought that, you know, that didn't seem right. I knew, my gut instinct told me it was going to be much, much lower than that. So, you know, we'll be able to calculate that in a minute. And then there's the temperature of the heatsink down the bottom, which we actually know, well, the differential, which was 13 degrees C from that difference graph we saw before. So let's see what we can come up with. Okay, so how do you calculate the total power that you're putting into your heatsink? How much, you know, waste heat is that those LEDs producing? Well, you can take the figure of, if you want to be on the real safe side, then you take the figure, the maximum figure, and not caring about the efficiency of the LED. So you assume the LED is 0% efficient, and in this case, each LED is 3.2 volts at 700 milliamps each. So they're drawing about 2.2 watts. So in the worst case, with a 0% efficient LED, there's going to be 2.2 watts of waste heat. But, well, you know, that's a little bit too crude. And I just, out of curiosity, I wanted to know what the efficiency of these new LEDs was. Now, if you look at the data sheet, okay, here's the data sheet. It doesn't tell you the efficiency. You think it might, right? Because it has on the front page here. I can put it up, but it says the available with typical efficacy of up to 132 lumens per watt. Okay, now that's not efficiency. Now you think, oh, that might be some Chinglish word or something like that for efficiency, but it's not. It's a different word entirely, and it's a trap for young players. Efficacy. It's different to efficiency. Now, this data sheet does not tell you how efficient these LEDs at all. It doesn't give you any information as to how much waste heat you're actually going to produce, lower than that. I mean, is the LED 10% efficient, 20%, 50%, 80%? What is it? Well, it turns out what you have to do to find that figure is you've got to actually look at a typical theoretical response. Here it is. Now I can put it up on the site as a better quality thing, but it's basically a lumens per watt response of white light, basically, and they're all the different colors of the white light spectrum, and you'll see that the maximum possible efficiency of a pure green LED or light source is actually 683 lumens per watt. Now, but because we aren't using a green LED, we're using a white LED. So you actually have to take into account the entire spectrum. And as it turns out, depending on how you actually calculate the eye response and stuff like that, it can be anywhere from, so we've got 683 lumens per watt. That's our maximum efficacy, not efficiency. Now, as I said, the white light spectrum, it can be anywhere from around about 300 to 350 lumens per watt, and that's for white light. So that's the figure. I'll take a value of 330 because, you know, that's a typical figure taken, I believe. So we'll take it, the maximum possible efficacy of an LED is 330, for a white LED is 330. And the data sheet for the Cree says it's doing 130. So what's that in percentage? You just divide it in and you get, bingo, 39% efficiency. That's how efficient these LEDs are. They're a hell of a lot more efficient than these, you know, a standard compact fluoro, which is, you know, down around, you know, 15% or something like that, 15 to 20. It's half of what it is, hence the lumens per watt figure. Now, I'll round that down to 35% efficiency because there's going to be, you know, some loss there. We'll round it down. So if we're powering this thing, putting 2.2 watts into it, the actual waste heat with the 35% efficient LED is 1.4 watts. And because I've got 8 of these mounted on the one strip, my total power is 11.2 watts. There you go. What was the point of that? Well, you know, I don't know, but it's interesting. Okay, so we know our total power going into the heatsink due to 8 LEDs is 12 watts. So we've got 12 watts flowing through our thermal resistance system here. So you can, and we know that the temperature differential on the heatsink down here is 13 degrees because we measured it, the difference on that graph which I showed you before. Now that means if you divide that into that, you know, you get approximately 1 degree C per watt for the aluminium strip, you know, based on the total system power and things like that. Now, well, that's pretty good, and it should allow us to calculate the temperature of the junction of each LED, but, well, I don't think it's going to be that easy because we no longer have 12 watts going into the system. We've only got 1.4 watts for the individual LED, and we based the calculation of this based on the total power of the system, and it gets all messy because we've got a strip like this and we've got 8 little LEDs on here like this, and so you've got multiple power sources coming into your system like this, and it's just it's all over the shop. It's messy. I don't like it. It sucks. And you know, you can do the calculations. You know, if you now got 1.4 watts for each LED going through, you know, this is going to have an 8.4 degree C rise above here, and you know, this is only going to have 1 degree or something like that. And well, what does it work out to? Well, bug it if I know, but it's not much. That's the thing. So what's the point of all this calculation? Well, we came to the conclusion that it's often just not worth doing thermal calculations because they're just messy, and or you could spend your whole life trying to analyze the damn things and it's not worth it. Oh. Now you want to know what a really interesting thing about these LEDs is that they're so darn powerful that that you can actually feel the light. You can actually feel the heat from the light, and it's not coming from the radiant heatsink. If you know, put these things on here, you remember at 35% efficiency, this is going to be putting out about at 2.2 watts. It's going to be putting out about 0.8 watts in that little tiny surface area in light. So there's 0.8 watts worth of light there. And if you put your finger on the heatsink, when this is mounted on the heatsink, the base of it, okay, it doesn't feel that hot at all. As we showed, it's only, you know, 5 or even 10 degrees above ambient. It's not much if you mount on a decent heatsink. It remains pretty cool. And then the base on top of that, you put your finger on that, and it's still quite cool. But if you put your finger over the LED and don't actually touch the metal, it'll burn you. You can't keep your finger on there. It's because this thing is pumping 0.8 watts of light energy into a couple of square millimeters of your finger. And it bloody well hurts. Now you've got to be really careful with these terms efficacy and efficiency, because often they're used interchangeably by people who don't know the difference, or they can actually mean the same thing depending on the luminous efficiency can be the same thing as the luminous efficacy depending on the context you're actually using it in, and it gets quite complex. So, you know, look it up and study it. It's quite actually interesting, the differences and how people, how you can work out efficiency versus efficacy and things like that over spectrums of light. It's a rather interesting aspect of engineering. Check it out. So what did I learn from all this thermal calculation rubbish? Well, not much at all, because when it comes down to it, engineering's often as simple as wetting your finger and sticking it on there. Is it warm? Nah, not really. She'll be right. Yes, I know everyone's going to write in and they're all going to say, oh, my model's wrong and I didn't do this, I didn't include that, and I got this wrong and that wrong. And, well, look, don't bother, because the whole point of it is that thermal design is messy and, well, sometimes it's just not worth doing. So, does it work? Okay, let's check it out. Ta-da! And yes, it does. Perfect. 16 Cree XPG LEDs. Perfect. Reflecting off the roof. It's a winner. I like it.